So now I've got maybe a slide or two on writing a Python code for the damp-driven pendulum. But mostly I'm just going to show you my code and we'll explore the features of the pendulum, the characteristics of the pendulum. So a couple of remarks. We're solving a second order ordinary differential equation. The equation in general, second order differential equation, has this form upstairs here, where the second order differential is in general some function of the dependent variable, the rate of change of the dependent variable, and the independent variable. And in our case, right, we have that exactly that situation. Here's the second order differential. So it's theta double prime in our case. Depends on the dependent variable theta, the rate of change of the dependent variable theta, and it depends on the independent variable time. So they're all over here. And so it's this equation that we want to solve. And if you remember, the basic way of going about solving a second order differential equation or n order differential equation is that you break it out for a second order into two first order differential equations. And so that's what you did for the mass spring problem and what we did for the falling body problem where you calculated the distance fallen. And that's what we're going to do for the pendulum. So basically, in our code, we're going to build this little column vector of the two dependent variables for our two first order differential equations, and a second column vector for the differentials of those two dependent variables that we're expressing the problem in terms of. So to make it concrete, this is what we'll do for the simple pendulum. So our two variables are theta and the rate of change of theta, so that's omega, the angular velocity. And the differentials of this little column vector of theta and omega, well, the differential of theta is omega, and then the differential of omega, which is the second order differential of the theta, is just that differential equation, that function over here on the right for our differential equation. So that's how we're formulating the problem. And then with that, we can use our, we're going to use our fourth order Runge-Kutta algorithm. We're going to discretize time and use the RK4 algorithm to propagate the position and the angular position, the angular velocity of the pendulum at time I to time I+1, and then we'll just repeat that to get the angular position as a function of time, the angular velocity as a function of time. Okay. So now I'm going to go to my code. So I need my function, my user-defined function, representing the fourth order Runge-Kutta method for calculating the dependent variable at time I+1 from the dependent variable at time I. So that's one function I need. And then I need a second function, a second user function, which is the user function that in the last classes would have been describing the falling body, the ordinary differential equation for the falling body, or the ordinary differential equation for growth or decay, or for a mass spring system. Now it's for the pendulum system. And so that's what's in this cell here. So this cell is just the Runge cutter fourth order from last class. This cell is, say, the free fall ordinary differential equation function from the last class, where I've modified it to represent the damp-driven pendulum. So remember, there's two differentials in here, because now our second-order differential equation is two first-order differential equations. This first differential is just that the angular position that the angular velocity is the rate of change of the angular position. So that's this piece here. And then this second differential is, I've written it out in these three pieces. This is just this second differential. This is the rate of change of the angular velocity, and it's got three contributions, right? One from the restoring force, one from the resistive force, and one from the driving force here. So I'm just bit by bit adding them together. I could put this in one line, maybe that would be better. Okay, so those are my two user functions. Everybody okay with that? See if it works. Okay, so now next cell. Some of these things will be very familiar. So first, I'm just defining some discrete time world universe. So I'm going to think about a period of 20 seconds. So that's TF. I'm going to divide it up into 500 intervals. And I'm calculating, the spacing between the individual discrete times from the 20 seconds divided by my 500. So that's the discrete time world that our pendulum is going to live in. Okay, then I'm going to just feed in some parameters of the damp-driven pendulum. That's this next little section here. So obviously the acceleration of gravity, the length of the pendulum. I'm just going to keep that as a 1 meter long pendulum. The mass of the pendulum bob, I made it 50 grams or 0.05 kilograms. And then I've got the parameters of the damping and the driving forces. So beta, for the moment, I'm going to switch off the driving force and the damping force. So for the moment, beta is 0, so there'll be no damping. And F, the driving force, that's going to be 0 too. So we'll just keep things really simple. I will print out, I show it here because it'll be a useful reference. The natural frequency of the pendulum is the square root of the acceleration of gravity divided by the length. So I'm going to print that out as a reference point. And I'll also print out the natural period. So the natural period is 2 pi divided by the natural frequency. So the period, natural period is 2 seconds here. And this is the frequency in radians per second. Okay, so those are the parameters of the problem. And then finally, I'm going to need some initial conditions. So if you have a first order differential equation, you need one initial condition. With a second order differential equation, you need 2 initial conditions to specify things. So that's going to be the initial angular displacement, the initial angular velocity. That's the theta naught and the omega naught here. So I'm actually here displacing the pendulum from the equilibrium by 0.1 radians, but I'm just going to release it from rest. There's no initial angular velocity. Is that all okay? Okay, so now this cell, we're going to do all the work basically. I'm going to make my array of times like we've done in the past from 0 to 20 seconds with these these 500 intervals with lin space in NumPy library. I'm going to initialize an array here to hold my coordinates for all those 500 discrete times. This is an array that is n by 2, because I've got two coordinates to keep track of, the angular displacement and the angular velocity. So this is why this is a two-dimensional array. I'm going to set the initial time, the initial angle and the initial angular velocity to be those two initial conditions that I set up here. So I'm just going to initialize those two array elements to my initial conditions. So that's that stuff. Then here's the actual calculation. All the calculation is done in this one little loop here, for loop. So here I'm going to walk through the times from that initial time where I know the coordinates to the final time. And I'm just going to calculate the angular displacement and the angular position at time j plus 1 from the angular displacement and angular position at time j. And I'm going to do that. I'm going to call that Runge-Kutta-4 user function. And that Runge-Kutta-4 user function in turn, by passing this argument pendulum, we'll call the pendulum user function that describes the pair of first order differential equations. So when I execute this loop here, we're going to have our calculation done. All the rest of this cell is just plotting the results. So these two lines here, this theta n and omega n, these are going to be my numerical solutions for the angular displacement and the angular velocity. And I'm just slicing them out of that two-dimensional array, that n by 2 array. The theta a and the theta omega a, these are a pair of analytical. I'm just calculating these analytically from the solution for a simple pendulum without damping and without a driving force. So they're just going to be kind of a reference for looking at our true solutions of the damp-driven pendulum. So I make two plots. One plot is theta versus time. So there's going to be, I'm going to have one plot, another plot. That's the upper plot. And the other plot is omega, the angular velocity versus time. So that's all I'm doing with these lines here. So let me run. Remember, let's go back here. So this is just a simple pendulum with no driving force, no damping force. And the amplitude that I started with, the initial conditions, where's that? Is 0.1 radian. So that's like 6 degrees. So it's a small oscillation. So this should be kind of the linear situation. Let's see, what am I doing? I think I already did that. I'll do it again. Let's run this cell. And so here's our results. So the top graph is angular displacement vertically versus time horizontally for that 20 seconds. The bottom graph is angular velocity vertically versus time horizontally along the horizontal for the 20 seconds. Why didn't the legend appear? Oh yeah, it did appear. The magenta line is this analytical solution for a simple pendulum. And the blue points are our numerical solution for the pendulum. I maybe should have said that. So the analytical solution is a solution of the linear second order differential equation. My numerical solution, you notice I put in sine theta. So it is the nonlinear differential equation that we wouldn't know how to solve numerically. Wouldn't know how to solve analytically in general. Okay, so here, you know, what are we seeing here? We're just testing a code that for a damp-driven nonlinear numerical solution that agrees with this kind of limiting case of when you have a linear oscillator with no damping and no driving force. So it's just a test of the code. So let's try some other parameters. I made myself a little table of parameters I might show you. Let's make the initial amplitude larger. Let's make it 10 times bigger. So this would take us from the world of a linear differential equation to nonlinear differential equation, where you can make the approximation that sine theta is theta to where you can't make that approximation. So now we're in this new world of nonlinear differential equations, nonlinear dynamics. And so if I run this cell here, we'll see, let's see what we got. Did I run this one? So this is the result if now I start instead of start swinging the pendulum like this, I start swinging it from this sort of angle. What we see is that simple feature of the linear differential equation, or kind of linear pendulum, that the period or the frequency is independent of the amplitude. This is no longer true. So now I've got a different frequency for my nonlinear pendulum, different period for my nonlinear pendulum. So you see that the angular frequency is larger, and that would mean that the period would be shorter. So the blue points are the numerical solution, the magenta is kind of the reference, and now I've got a larger angular frequency, which is a shorter period. And you can see it in angular position versus time, also angular velocity versus time. So that's an interesting feature. We've sort of, especially for timekeeping, that if you swing the pendulum from this high, it won't have the same period, won't have the same frequency as small amplitude oscillations. So that's nonlinear dynamics entering into our problem that we can see in the numerical solutions. We couldn't have seen in an analytical solution very easily. Let's switch on the damping force. So I think I'll go back to, I'll go back to small oscillations so we don't have to worry about that. And I'm going to switch on beta. Now, as a reference, right, we said that there's these three cases of under, critical, and over damping, depending on the value of beta being smaller, bigger, or the same as the natural frequency. So let me start with the value of beta being 10 times smaller than the natural frequency, which was 3.1 radians per second. And this is our result. Okay, so this is the effect of damping from a numerical solution. Remember, the magenta is still just the old simple pendulum with no damping, no driving force. And so in blue, you see that the oscillations are damped out with time, decrease with time. You see that the, also probably see, I think you can see it, that the frequency is slightly different from the undamped frequency. Not very different, because if you remember, the damped frequency is equal to the square root of the natural frequency squared minus beta squared. So beta is kind of small, 10 times smaller. So that correction is sort of scale of a part in 100, but it is slightly different. And so that's the effect of damping. We're calculating that. So what's interesting for the damping is to look at these different cases. So let's now make it critically damped. So that's when beta equals the natural frequency. So beta is now going to be 3.3. And so now you see this case that I mentioned, when you got critically or overdamped, you don't get the oscillations. The pendulum bob will just glide back to the equilibrium with some characteristic time scale. And so that's what we're seeing here in the angular position, just the glide back to the equilibrium. In the angular velocity, you see, we released it from rest, so it has to speed up to get back to the equilibrium, and then it will slow down and stop at the equilibrium. And so that's what we're seeing there. It's interesting to compare that with overdamping. So if I made this 31.3, so it's 10 times the critical damping, and then we run that. This is the case of overdamping. So it does eventually get back to the equilibrium, but it gets back to the equilibrium at a much slower rate than critical damping. So here you see in the top plot, right? It gradually working its way back to the equilibrium, just gets there probably by 20 seconds, the far right in the plot. You see that the angular velocity is very small compared to critical damping. So it just crawls its way back. And so that, as I mentioned, critical damping is often used in mechanical systems if you want to damp out some vibration, some oscillation. You want critical damping to damp it out quickly. If you overdamp, it returns to equilibrium much slower. Okay, what am I doing? I want to look at the driving force next. And what I'm going to do, we want oscillations. So I'm going to put this, I'll leave the damping in, but I'll put it at 1/10 of the natural frequency. And then I'm going to look at some cases of the driving force. So we'll look at that. So the interesting thing about the driving force is if the frequency of the driving force, that's omega f, is equal to the natural frequency of the pendulum, that driving force will drive large oscillations. That's resonance. If the frequency of the driving force is far from the natural frequency, then you can have a large driving force, but if it's far from the natural frequency, you only get small oscillations. And so that's a very interesting feature of resonance that comes out of the application of the driving force. So first, I think I'm going to show you a couple of cases where the driving I'm going to make it 2 times larger than the natural frequency, and I'm going to make it 2 times smaller than the natural frequency. So we're not on resonance. And then we'll go to a couple of cases where we are on resonance. So I've made the driving force non-zero here, and I've made its frequency twice the natural frequency. Let's try this, see what we get. Okay, so what are we seeing here? Remember the magenta, actually, let me just change later on. I think this is a big driving force. We'll compare it with a small one. Okay, so we're applying this driving force. It's twice the frequency of the natural frequency. And we're comparing it with the simple pendulum where there was no damping or driving. So the simple pendulum is just the magenta curve. And the blue dots are the numerical solution with the damping force and the driving force. What do we see in the numerical solution? Firstly, if you look over here on the left, you see a period in which things are changing. So this is this transient region. The way we think of this is that suddenly we switched on the driving force, and the pendulum that had a natural frequency of omega is going to evolve to oscillate with the driving frequency, omega f. So that this transient period on the left-hand side. But if you look at the last 10 seconds, right, now let's go over here on the right-hand side of the two plots. Now things are very stable for the angular displacement or the angular velocity. So this angular velocity, this angular displacement is now oscillating at, this is the driving frequency. You see it's twice the natural frequency in magenta. And so you're seeing that after you go through that transitory period, then you see oscillations of the pendulum system with the driving frequency. Just to make that clearer, if I change, supposing instead of making the force frequency twice as big as the natural frequency, let me make it half as big. Now you see, right, here's again, let's on the far left is this transitory period where the numerical solution looks kind of complicated in its shape. But if you look over on the far right for the numerical solution, now you see, again, simple oscillations with the driving frequency. The driving frequency is now half the natural frequency. So the period is twice as long and the frequency is half the size. So that makes sense. And now let me just show you, let's go towards resonance. So I'm going to put this frequency very close to, it can't be exactly, but very close to the natural frequency. See what we get here. We get this situation here. So the magenta curve is the same every time I make this plot. So now you see, now I'm near my driving frequency is near the natural frequency. I get massive oscillations. And that's because I'm now on resonance. So the thing is oscillating dramatically. Okay, those are the cases I wanted to show you. Any questions on all that stuff?